All right, let's talk titration. So titration, you're all a little bit familiar with it. We talked about them way back in December. We did one a week ago. So basically, a titration can have several purposes, but the main one is to find the concentration of a solution when you don't know its concentration. You can titrate it. And there are different kinds of titration. We'll do acid-base titrations. In a few weeks, we'll do a redox titration. The other thing you can get out of a titration is you can find the strength of an acid. All right. So we'll talk about those two different goals and how we reach them. In general, you know the setup. You've got a beaker or a flask at the bottom. We have words for these things. So down here, we call this the analyte solution. In other words, the one being analyzed. The stuff that's up in the burette we call the titrant solution. And you want to know the concentration of your titrant solution. You want to know the concentration of your titrant solution. So when you're adding this solution, you want to know what its concentration is. The one down at the bottom, usually you don't know the concentration. That's why you do the titration. So the question is, isn't it to find the strength of the acid or base? Now, to find the strength of the acid or base, we are going to need to measure pH as we do the titration. So what you did last week was a titration where you didn't measure pH. You just put an indicator in that would change colors when you reach the equivalence point, when you had added equivalent moles of acid and base. What we're going to do today is really look at what happens to pH over the course of a titration. We'll see why the indicator would change color when you reach that equivalence point. So we're going to start by looking at strong acid and strong base. And then we'll look at what happens with a strong acid and a weak base. All right, so let's do this. This is going to be practice with pH calculations. So the first thing we'll consider is when we titrate a strong acid with a strong base. We want to know what will happen to the pH of the solution as I titrate it. So we first need to ask ourselves, well, when I have a solution of a strong acid, say HCl is probably the simplest one, and I'm adding NaOH, what's the reaction? And since all acid-base stuff goes to equilibrium, I want to think about what's its equilibrium constant. Okay? So, what is the reaction that happens when I add NaOH and HCl together? Daniel? All right. Can anyone think of a simpler way to represent that equation? Yeah, we know that HCl is completely dissociated, and we know that NaOH is completely dissociated in water. And we know that NaCl is completely dissociated in water. So the Na plus and the Cl minus are just spectator ions. So really, the reaction is just H plus OH minus makes H2O. Has anyone seen that reaction before? And does anyone know the K value for that reaction? Chirp, 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 chirp. Not quite. You're along the right track. All right, why don't you get out Lecture 17 notes? This is really the reverse of the Kw equation. Right? Kw was when water splits up into H plus and OH minus. So this is the reverse of the Kw equation. So K for this reaction is going to equal 1 over Kw, which is going to be 10 to the positive 14th at 25 degrees Celsius. So K is 10 to the positive 14th. What does that tell me about this reaction? Forward reaction is very favorable. So it's pretty much going to go almost to completion. We're going to use that when we try and analyze what the pH is at different points in the titration. All right, so let's just start by saying, let's say I have 50 milliliters of a 0.2 molar solution. What's my original pH? Well, how do I find the pH of a solution of HCl? Well, what's the definition of pH? Negative log of concentration of H plus. So if I want to find pH, I need to find concentration of H plus. So if I have an HCl solution and it's 0.2 molar HCl, how do I know how much H plus that gives me? What do you know about HCl? Not 1/2. What do you know about HCl? Completely dissociates. So I get 0.2 molar H plus and 0.2 molar Cl minus. Which part of that do I care about? The 0.2 molar H plus. So really my pH is going to equal the negative log of 0.2. So everybody get out your calculators. I had a professor in college who required everyone to learn to do logarithms in their head. And he'd call on students at random and say, oh, what's this logarithm? All right. Negative log of 0.2 is... All right. All right, so that's my initial pH. That's where I would be starting out in this titration. Really low pH. Makes sense. We have a strong acid, relatively concentrated. So now let's say I start my titration, and I'm adding NaOH to this solution. So I'm titrating a solution with 0.2 molar HCl, of 0.2 molar HCl, and I'm adding 0.2 molar NaOH. So I want to know what's the pH after 5 milliliters of 0.2 molar NaOH has been added. This is actually a pretty complicated question. This is where we're going to go back to our reaction that we know is occurring. So a reaction that we know is occurring is H plus OH minus makes H2O. We pretty much said this reaction is going to go to completion. Now, how am I going to fill in my chart? Things get a little bit tricky here. So I have 0.2 molar HCl, I have 0.2 molar NaOH. Should I put in initial values of 0.2 and 0.2? Do I have the same amount of HCl and NaOH? No. When you're adding solutions together, the tricky part is you're going to have to do all your calculations in moles and then convert back to moles per liter later. Now we're going to be dealing with small numbers of moles. So I'm going to make my life easier by doing this in terms of millimoles. So I'm going to fill in my chart in terms of millimoles. So let's see. Initially, I have 50 milliliters of 0.2 molar HCl. So to get the number of millimoles I have initially, I'm going to use 50 milliliters times 0.2 moles per liter. So that gives me, what, 10 millimoles of HCl. And I have 5 milliliters times 0.2 moles per liter of NaOH. So I have 1 millimole of NaOH. So you could do the whole thing in moles, it's just your numbers would be 0.01 and 0.001. So millimoles are a lot of times more convenient to use. All right, so I will fill in for H plus 10, so I have 10 millimoles of HCl. For OH minus, 1. For the H2O column, I'm just going to cross it out. Why am I crossing out the H2O column? That's what everything's dissolved in. That concentration is the same, and remember, in equilibrium, a pure liquid, a liquid doesn't factor in. So I have 110. What's my limiting reactant? OH minus is my limiting reactant. So when I make this reaction go to completion, what's the change in OH minus concentration? -1. That'll also be the change in H plus. So this will be 9 millimoles of H plus and 0 of OH minus. All right. Now, the amount of OH minus left at equilibrium will have to be, some number. But I don't really care. What I care about is H plus. Remember, to get pH, I need concentration of H plus. So I have 9 millimoles of H plus. How am I going to turn that into a concentration? So after this reaction, 9 millimoles of H plus. Well, divided by, well, I want to divide by the volume, but what's the volume now? Oh. 55 milliliters, yeah. All right, so 9 over 55. Notice when you use millimoles and milliliters, the millis pretty much cancel out, so you get moles per liter. So 9 millimoles per 55 milliliters is, sorry? 0.164. So then pH is going to equal the negative log of, this is moles per liter. pH is going to be the negative log of 0.164. 0.785. All right. So what we're looking at is what's happening to pH as we titrate. We started at 0.7 essentially, and now we're at 0.785. Not a huge change. So we started our titration, and the pH went up a little bit. Let's keep going. This time I want you to follow this same process, but now let's consider what happens after I've added 25 milliliters of 0.2 molar NaOH. So again, it's the same reaction. Again, it's going to go to completion. You just have different amounts. So take some time and fill that in. All right, for the second one, how many millimoles of H plus am I starting with? 10. In fact, in all of them it's going to be 10 because I'm starting with the same original acid solution. But in this case, how many millimoles of OH minus do I have? 5. It was 0.2 moles per liter times 25 milliliters. You give me 5 millimoles of NaOH. All right, so I have 5. I don't care about the water. Still, my limiting reactant is OH minus. So you should have had minus 5, minus 5. I still have 5 millimoles of H plus. So I can stop there, calculate the new concentration, calculate the new pH. So how do I get the concentration of H plus? Now the total volume has changed to 75 milliliters, so it's 5 millimoles over 75 milliliters. And that is 0.0667. Sure. So the pH is going to be the negative log of that, which is 1.18. All right. All right, if I do the same thing at 45 milliliters, right, we're just tracking kind of periodically so we can get a sense of what's happening to pH. Seems like pH goes up a little bit more. At 45 milliliters, I'm still going to have 10 millimoles of H plus to start with. If I had 45 milliliters of the NaOH, how many millimoles of OH minus is that? 9. All right. Cross out my water. OH minus is still the limiting reactant, so minus 9, minus 9. So now I have 1 millimole of H plus. What's my new total volume? My new total volume, 95 milliliters. 1 millimole in 95 milliliters is 0.011. So the pH is going to be the negative log of that, which is 1.98. All right. All right. So far, pH has gone up some, but not a ton. Let's add 5 more milliliters. See what happens. So if I am adding 50 milliliters, I start with 10 millimoles of H plus, and how many millimoles of OH minus? 50 times 0.2 is 10 millimoles of OH minus. So who's the limiting reactant? And they both are. Minus 10, minus 10, 0, 0. So the pH is now going to be the negative log of 0. No. So what do I do? All right. So one logical way to look at it is, we've gotten rid of all the H plus and the OH minus. So now this is essentially neutral water. The pH is going to be 7. Yeah. pH is going to be 7. One way to prove that is to say, well, in all these previous cases, we went to completion and didn't bother sending it back at all because we know it only comes back a tiny bit because K is so big. But in this case, since everything's 0, we could send it back a little bit and say, all right, when I come back, and then go to equilibrium, this will go up by x, this will go up by x, and so I have x times x. And I can just set up my experiment, my equilibrium expression for Kw, which is concentration of H plus times concentration of OH minus. So that's going to be x times x. Set that equal to 10 to the negative 14th, and I know x is going to equal 10 to the negative 7th. So the pH will be the negative log of 10 to the negative 7th. So the pH is now 7. So far in our titration, we were adding acid, pH going up a little bit. Adding base, pH went up a little bit, a little bit, a little bit, a little bit. These last 5 milliliters, we went from 2 to 7. What if we add 5 more milliliters? What's going to happen? Well, let's try it out. H plus OH minus makes H2O. Starting with 10 millimoles of H plus. How many millimoles of OH minus? 11. 55 times 0.2. Who's the limiting reactant? H plus. So this is going to be minus 10, minus 10. Now instead of having leftover H plus, I have leftover OH minus. So I think the easiest thing to do now would be to calculate the POH. and then just convert that into pH. So to get the pOH, I need the concentration of OH minus. So I have 1 millimole of it. What's the total volume? 105 milliliters. So that's going to be like 0.009 something. What do we get? 0.0095. All right. So the pOH will be the negative log of 0.0095. .02, and the pH is going to equal 14 minus 2.02, which will be about 12. So let's summarize how our titration went. Oh, sorry, I wanted to do one more point, just so we could see what happens at the very tail end. So we might as well do that. After I've added 75 milliliters of NaOH. How many millimoles is that? 75 times 0.2. 15. All right, so 15 millimoles. H plus is the limiting reactant, so minus 10, end up with 0, and now 5 millimoles of OH minus. So the concentration of OH minus is going to be 5 millimoles divided by my total volume, which is now 125 milliliters. So that's 0.04 moles per liter. So then pOH is going to equal the negative log of 0.04. All right, so this is going to be 1.4. 1.4. So then this pH is going to be 12.6. All right. So hopefully the calculation wasn't too mind-numbing. But this is the kind of stoichiometry stuff you want to be able to do relatively quickly. All right. So let's summarize. Let's put our points together. So let's gather up our points. At the start of the titration, the pH was 0.7. So 0 milliliters added, pH was 0.7. After 5 milliliters, it was 0.79 essentially. After 25 milliliters, all right, it was like 1.17. After 45 milliliters, after 50 milliliters, it was 7. After 55 milliliters, it was 12. After 75 milliliters, it was 12.6. So if I were to make a graph of pH versus milliliters of NaOH added. What would that graph look like? Well, when we started out, pH was low. And it was kind of increasing slowly, slowly, slowly. And then we got to right around 50 milliliters, and what happens? It spikes way up. And then after that, kind of leveled off again. So this point right here, where the pH was 7, that was where we had added 50 milliliters. And the big jump really occurred within 5 milliliters on either side of that. Right? So in the lab last week, we were using phenolphthalein as an indicator. Phenolphthalein has a pK of about 9, so it changes color around pH of 9. So notice all this first part of the titration, where the graph was pretty flat, we're not going to see any color change in our indicator because the pH is changing a little bit, little bit, little bit. Only once we pass this middle point are we going to see the indicator change. That's the goal when you choose an indicator, is you want one that won't change until you reach that jump in the middle. And once you reach that jump in the middle, you want your indicator to change. Okay? So we have names for these for this point in the middle where we had an equivalent number of moles of acid and base. Here we had equivalent number of moles. 10 millimoles of H plus, 10 millimoles of OH minus. So we call that the equivalence point. And at the equivalence point, we have the same number of moles of H plus and OH minus. Yeah. All right, good question. The question was, does the equivalence point always have to have a pH of 7? Well, when you have a strong acid and a strong base, you have these two armies that are both strong. When you've added equivalent numbers of ions on each side, they will always fight to a draw. So when it's a strong acid and a strong base, yeah, the pH at the equivalence point will always be 7. But if one of them is weak, then when you reach equivalent numbers of moles, the weak one is always going to lose. And so the pH won't be 7 if you're using a weak acid and a strong base, or a weak base and a strong acid. One side will win. Yeah. All right, so that's a strong acid, strong base titration. And we basically just walk through why it does what it does. Why do we see something happen right when we get equivalent numbers of moles? Because that's where suddenly the balance of power shifts in the solution. What questions do you have about titration or any of the calculations we just did? The question is, what's the conversion from POH to pH? So pH plus POH equals 14 at 25 degrees Celsius. You should always assume it's at 25 degrees Celsius unless you're told otherwise. the reason we say at 25 degrees Celsius, that's the temperature when Kw equals 1 times 10 to the negative 14. If you go to a different temperature, that's different, so all the rules change a little bit. What else? So the question was, what was the pK of phenolphthalein? So yesterday we talked about indicators, and phenolphthalein, or yesterday, I forget. But previously we talked about indicators, and phenolphthalein has a pK of around 9. So phenolphthalein will change color when the pH is around 9. So notice when we get to the equivalence point, the pH is 7. So the phenolphthalein hasn't changed color yet. But when you add one more drop, the pH shoots up. I mean, we can see we calculated for after we've added 5 more milliliters, and by then the pH was already up to 12. So basically, when you go one drop past the equivalence point, that's where it's going to change colors. A better indicator for that titration may have been bromothymol blue, which has a pK of about 7. So it does change color right in that 7 range. But phenolphthalein did the trick. Using an indicator, it all kind of depends on what your goal is. And if you're measuring pH along the way, the indicator becomes superfluous. So we're going to do titrations after the test where we where we measure pH the whole way, and so we can make our graph. And so we'll be able to see from the graph where the pH changes rapidly, so we can find our equivalence points that way. Other questions? All right, I think we're going to call it a day there. I think we'll save weak acid, strong base titrations for a week from now.